Hello everyone, welcome to the third devlog here. I'm working with Emily on this little game that we're making, and I wanted to go over how we've implemented mouse picking. So when you're mousing over an entity, we recognize that and show a little overview, or you can click on it and get some dialogue or what have you. And the interesting part about this is that it's a pixel perfect mouse picking, so you have to be mousing exactly at that particular pixel. That might not be the best idea for the gameplay in general, but it's much better than, for example, just checking against the entire texture, because the texture goes from this point here all the way to this point here. So if the mouse was here, it would already be overlapping with the old lady, and we obviously don't want that. So this approach makes it a lot better gameplay wise for the time being. Then we can make it better later on. But I wanted to go over how we've implemented this. It's surprisingly simple to do if you're working on Metal with the Metal API. It's less simple to do if you're working with OpenJava and things like this, but I don't think it's particularly hard either way. This is a very well-known approach. If you search for mouse picking using GPU, that's most likely the approach that is going to come up on Google or what have you. So I'm just not gonna focus too much, but I'm gonna give you an overview, show the code, and all of that, because I think it's quite useful to have a video explaining and some actual code instead of just an answer on Stack Overflow or what have you. So let's first do a Metal capture. If you're working on Xcode and Metal, you can use this button here, the button with the M, and do a capture. That basically captures an entire frame worth of GPU data, of all of your drawing commands, all of your drawing data, and you can see the timeline of your frame, which is really useful. So you will note here that we have two textures. We have the color texture. This is what is displayed to the monitor. This is what the user will see. But we also have this texture here, which is named GPU picker text. And this is the texture that we use to implement the feature. The feature. You see here that whenever we render to a sprite, we render to both the color texture and to the GPU picker texture, and we just render everything to both of those textures. The difference is that whilst this one holds the color that we read from the texture and the sprite and all of that, this one renders something else. This one holds an integer value which represents the ID of the entity that was rendered into this pixel. So every pixel that has a color also has an ID associated with it, and the ID is the ID of the entity whose color is in the color buffer. The color buffer being this texture here. And when we want to check if the mouse is overing a particular entity or who's the mouse over, we can just sample this texture here on the CPU, and that gives us the ID of the entity at that particular place. And that's how we know that the mouse is over the old lady, or the mouse is over the flower pot, or what have you. To do that, we need to first send data from the CPU. The CPU holds the ID of the textures that we're going to render and all of that. We need to send data from the CPU to the GPU. The GPU is going to render that into the texture, and then we need to copy that texture from the GPU to the CPU, so that in the next frame the CPU can check whose pixel holds whose ID and get that all done. So to do that, we have this sprite instance data. This little struct holds the information for every sprite that we render. So anything that you see on the screen has one of these, an instance of this struct associated with it. That gives us the color, which most likely is going to be white, because we want the texture to be rendered using the color that came from the texture sprite. The tint color is a multiplier, so if it's white, it's all ones, and you multiply anything with one, you get the thing that you multiplied, which makes it the color. But if you wanted, for example, to render the text we render with the tint color of black. That will make the texture black, the text black, or we can make it red, or any color we want. It has a starting atlas, ending atlas. This is just so that we have a texture that has multiple little sprites in it, we can render a particular region of that texture. But important for us is the small speaker ID. This, at the moment, is just the ID of the sprite. It can be any number you like, right? You can put, for example, 999, and you can check for a particular, you can see, oh, is the mouse over entity ID 999? That means that this needs to happen, right? So you can put arbitrary numbers in there. But for our particular case, we use the ID of the texture. The ID of the texture is just a hash of the full path to that texture. So the old lady lives in a file. We're just going to hash the path of the file, and we get an ID. This is just a very straightforward way to get a unique ID for any particular sprite in the game. So you don't need to actually do any ID generation. It's always unique, and it doesn't really it doesn't take much effort to do that. So at the moment, it's just the hash of the sprite, but it doesn't really matter. So each sprite that you see on the screen has one of these associated with it. So we basically send this data to the GPU, and on the GPU, we use this data to render into the texture. And how do we do that? So first, let's show how we create that texture, which is going to be here. To create a textural metal, you need to use a metal texture descriptor. This is just the helper struct that tells metal the properties of the texture that you're requesting. This just makes it easier for the API. It doesn't really matter much how you do it. Metal decided to do this way. I like him personally, but it's irrelevant. In here, we just tell it that we want a texture that has the same resolution as the game. That will make it simple to sample in the GPU, but I'll explain that a little bit later. It has the same resolution as the back buffer, as the texture that we're going to render. It has a pixel format. The pixel format that we picked was a single channel, so just red instead of RGB or what have you. It's a 32-bit value per pixel, and is assigned integer. So basically, every pixel on that red texture that we saw, every pixel on the mouse picker texture can hold an integer value, which is very useful for us because our ID is an integer value. It's a 2D texture. That's fairly straightforward. It has an X and a Y, so it's a two-dimensional object. It is a texture that we want to read from. I don't think we necessarily want the sample one, but I put it here because I just copied this code from other places that I was using it already. Then we ask the GPU, which is the metal device. The metal device is just metal's representation of a GPU, right? So you can have multiple devices if your computer has multiple GPUs, but you just create the default one that will give you the GPU. If you work on a laptop, that will give you the default GPU. And you can ask it to create resources for you. In this case, we're going to create a texture, given the texture descriptor. We set a label to it. This just makes it easier to see here in the metal capture. And then we guard the little guy. We just cache that variable, that into a global variable that we can use later. And we use it here. So this render one frame is basically where we render the entire scene that you saw, right? This function is where we emit all of the render commands, render this sprite here, this sprite there, and all of that. At the beginning of it, we are going to attach two textures to the render path descriptor. A render path is just you can think of a render of the scene, right? You're going to render from beginning to end the scene with all of the resources, everything that you want to be seen. That's a render path. You can have multiple of them. For example, you can have one that renders the color, one that renders the normals, one that renders whatever else, and then you do something with the different textures that were generated from that. But for our case, we just have a single render path. And we are going to render to two textures at once. We're going to render to the back buffer, and we're going to render to the mouse speaker. The back buffer is just the back buffer of the double buffer system that most games use. So most games are going to use two buffers, two color buffers, two things that you see on the screen. One is the front buffer. The front buffer is what your monitor is always seeing, right? Your monitor is seeing the front buffer. You don't want to change the contents of the front buffer whilst your monitor is displaying it. That's how you get screen tearing. You can just start screen tearing. You're gonna see what the effect looks like. That effect happens because you're changing the contents of the front buffer whilst your monitor is accessing it, and so you get two separate pieces of data, two separate systems accessing the same data at the same time, which is never good. So that's solved by using two buffers, which is called double buffering. You're gonna have the back buffer. That's why your game is writing 2 whilst your monitor is displaying the front buffer. When your monitor syncs with your game, which is called vertical sync, is basically when your monitor tells your game, I'm about to render the next frame. Your game can tell, oh, so you rendered this texture, and then you tell it to render the back buffer. The back buffer basically becomes the front buffer, and the front buffer becomes the back buffer, and you just go on like this. So the color we want to render to the back buffer, right? And we say that that's the 0th texture. That's the first texture that you're going to render to. And then we also want to render to the mouse speaker target, which is that texture that we created at the start of the game. And they say that we want to reference it using the number 1. They'll have to be matched in the shader, and I will show that later. Then we come here, we emit all of the drawing commands, and we wait for it to finish. The reason we need to wait for it to finish is because we are going to read from that texture to copy the texture from the GPU to the CPU, so that in the next frame we have access to the data from the previous frame. And so we need to wait for it to render before we can read from it. After the GPU finished rendering, we can get the bytes. We can basically copy the data from the GPU back into the CPU. The CPU has this memory picker bitmap. This is just a sequence of bytes that are large enough to hold all of the data that comes from the GPU, right? This is just a bitmap. It's just an array of bytes that are interpreted as a color. That's what a bitmap is. A bitmap is basically an image. So if you have a PNG, for example, after you decompress the PNG, you get back a bitmap, which is just the raw pixels of the image. And we have one here for the texture. It's just a storage that we use to copy data from the GPU to the CPU. So after we copy all of the data here, right? And let me explain this real quick. So this is just what's called a stride. A stride is basically how many bytes do you need to go from one row of the texture to the next row of the texture. And if you think of a texture as a 2D thing, right? If you look at a 2D image, from one row of that texture to the next row of that texture, you need to skip all of the bytes of the front of the first row, and then you get to the second row. And you skip all of the bytes of the second row, you get to the third row. So to skip one line, which is called a stride, we need to skip however many bytes we have per pixel. In our case, we have 32 bits, which is the size of this mouse speaker reference ID. So this number here will be 4, because it's 4 bytes, times the width of our texture. That will give us how many bytes we need to offset our pointer to go from one row to the next row. And we tell method that we want to get the texture from the entire texture. 0, 0 is the start, width and height is the end, and that's the region that we want to read from. So after this point, we have the data on the CPU. It is currently on the frame data for the render thread. So we have two threads. We have the simulation thread and the render thread. You can think of this as the front buffer and back buffer. It's very similar to that. Whilst the simulation thread is doing work to generate the current frame, the render thread is doing work to render the previous frame, right? You can think of this very similar to a back buffer and front buffer situation. And so when the render thread copies the data from the GPU to the CPU, it writes to its own piece of memory. When we flip the buffers, the render thread data becomes the simulation thread data, which means that the next frame, the simulation thread, the gameplay code, will have access to the mouse speaker texture that we rendered on the previous frame. So every time you're sampling the mouse speaker texture, you're getting the data, you're getting the where the entity was one frame ago, last frame, essentially. If you're running it doesn't really matter the frame rate you're running. This pretty much makes it invisible. It doesn't really matter because you're always rendering last frame. Because the current frame hasn't been rendered yet, what the user is seeing is the previous frame. And so because you're using the previous frame's data, you're sampling the data that the user is currently seeing, which is exactly what you want. And so in the gameplay code, what we do to sample the texture, to get the entity that the mouse is over, we get the bitmap. This is the same bitmap that we just wrote it to. Just copy the GPU texture into this bitmap. This is what we have here, and we need to sample it. We need to access the data in it to get what is the entity under the mouse. Because our mouse picker texture has the same resolution as our color texture, the mouse position, if we have the mouse position inside the color texture, we also have the mouse position inside the mouse picker texture. And that's the position here. This is the mouse position relative to the color texture. So for example, if the mouse position is at the very bottom left of our color texture, of our window if you will, it's not quite the window, it's the actual content being shown on the window, but you can think of it as the window. If our mouse position is at the very bottom left, this value will be 0, 0. If the mouse position is at the top right, this value will be 1920 by 1080, for example, if you're rendering the game at full resolution, full HD. Or if you're rendering 4K, it will be 3200 and something by something, right? And because our color texture and our mouse picker texture have the same resolution, this position here is the position of the pixel that we want. And when to get to sample the texture, we need to do a little bit of math, and that's because the texture data is actually a 1D piece of data, even though the texture is 2D. That's just so that it's more efficient, because you only need to allocate one piece of memory, and you can hold the same amount of information than if you had allocated many different pieces of memory. For example, if you wanted to do this in 2D, you would allocate one array per row of your texture, and then you would access an array of arrays to get access to that particular pixel. But because we want to be at least slightly efficient, we have just one buffer, and that buffer holds all of the texture, all of the data for the texture. And so to get the particular index, the index for a particular pixel position, we need to flatten. It's called a flatten operation. And to do that, we're going to multiply the Y of the mouse by the width of the texture. Like I mentioned before, this is going to offset the mouse position from, say, 3, because we want to go to row 3. Is going to offset that 3 is going to offset by the amount of bytes required to go up 3 rows in the texture, or down 3 rows in the texture, if you're thinking of it as the top left being 0, 0. And then you just sum the X position of the mouse. That's the column, right? The column always goes is very simple. The row is the one that requires a multiplication to be correct. And so you get the pixel position in 1D, and you can access that, and that gives you the mouse picker reference ID. Now let's talk about how the data went from CPU originally to GPU, right? How did we go from sprite instance data? How did we go from here to here? You're gonna see here we have this buffer. This is a GPU buffer. This is a metal buffer, which means it's just a piece of memory on the GPU, and we just allocate that piece of memory, and it just leaves it just exists throughout the game, and we just, every time we're going to render something, we put the information that we need in there, and we literally just copy from sprite. We just copy the data from here into that buffer, and that buffer is now accessed on the GPU, right? And the copying will happen. Let me see if I can find. Let me see. The copying will happen here. So we get the contents of the buffer. This is a pointer that we can write to on the CPU. And that's the pointer. Ignore this bit here. This is about instance rendering, because we use instance rendering. It's a little bit more involved than if you just had a simple buffer, but it's the same thing essentially. We're just gonna copy the memory from the instance data, which as I mentioned is that. We're gonna copy from that to the GPU buffer before we render anything, and that will make it accessible on the GPU. On the GPU side, it's gonna show up as this thing here, instance constants. This is that buffer that we copied the data into. It's accessed in here. We have access to it in the shader code. And in the shader code, you see this mouse speaker ID. That's basically the mouse speaker ID, which is the same as the data that came from here. Okay? And we set to these properties here. So this here is how we tell the GPU where to render what, essentially, which texture to render which data. Because like I mentioned, we are going to render to 2 textures at once, and you need to tell the GPU what to render on which texture. And you can put these attributes here. The color 0 means you want to render to the texture, whatever texture is currently bound to color attachment 0. And color 1 means that you want to render this value to whatever color attachment is bound to color attachment 1. 0 is, if you remember, color attachment. If you remember, we have it here. Before rendering the frame, we bound the back buffer to color attachment 0, and we bound our mouse speaker target to color attachment 1. And they show up here as color attachment 0 and color attachment 1. Okay? And in the shader code, we want to render the color of the pixel to color attachment 0 and the mouse speaker ID to color attachment 1. And that's how you render to both of those textures at once, and that's how you tell the GPU which data to render to each texture. And this data is then copied to the GPU, to the CPU like we talked about before, and then sampled on the CPU to get the entity that is currently under the mouse. And that gets us back to where we started in here, where you get mouse pixel, mouse perfect, mouse picking. So that's how you do that using Metal. This is the simplest possible way of doing it, which is often the most inefficient way of doing it, but it is very straightforward and you can get it done quite quickly if you have experience with Metal. If you have any questions, you can put it in the comments below and I will try to answer them, or if you require if you'd like to see a more in-depth tutorial going through the code, perhaps writing this feature in a video, I can do that. And that's how we've done it. I hope this was enjoyable or informative, and I'll see you later.